Okay, so you probably already know that strings are just laid out as characters in memory. But what's important is each string has an index, starting with 0. And you can actually access strings as though they were arrays or vectors. And using the same functions. So if you use the at function, which is what we recommend, then it will return the character at that index location. And again, there's 0 indexed. You can also use array notation with them. Let's see, they're all using at here. So I'm not going to show you that. At is the better way to access an index, and the reason is if you are out of bounds, it will throw what we call an exception, something you haven't dealt with yet, but will in a couple weeks. Your program will terminate. And that's a good thing because otherwise you would get some invalid value, but the program would keep running and the output would look strange, but you wouldn't know why. So we definitely advise using at as opposed to array notation to get at individual characters. And then the same thing, if you want to replace a character, you can also use the at function with an index and then say equals. Okay. Size returns the size of the string or the length of the string, and you'll see length, they're the same thing. So string and length are the same thing. Okay, that gets me through that part of it. And then, where I really want to get to, not character operations, although those are nice. I want to get to substring and find. So these two functions very handy. In fact, in a couple weeks in the labs, you are going to be doing a problem that is going to involve the find and substring functions. So find takes a substring like me, and it returns one of two values. Either the index location where that substring first occurs, or something called string NPOS, which means at no position was it found. So you might think it would return -1 or some other value. It actually does return an integer, but you don't know what that integer is. It's defined as string : NPOS. Okay, so as an example, if you have user text of help me, so here's the value help me ! And you try to do a find on me, it returns 5 because if you count over, H is 0, E is 1, L is 2, P is 3, the blank space is 4, that counts, M is 5, so it returns 5. Okay, if you're looking for a Z, it returns string : NPOS. It's a constant. Don't put that in quotes. Okay, it is actually a defined integer. So don't put that in quotes when you're testing for it. Okay, substring will return a substring that starts at the given index with this length. So for example, if my text is this, and I ask for the substring that starts at index 0 and has 7 characters, I get HTTP : greater than. If I'm looking for the last 4 characters in the string, I go for the size -4 and ask for 4 characters, and I get .com. Okay, these are two very helpful functions that you will, these are methods associated with a string. Notice that you give the variable and then dot find. So it's not find parentheses name of the string. It's string dot find. Okay? Questions associated with that? Okay, you have a challenge activity. Actually, before we, let's see. What is the challenge activity I want you to do? Not that one. And not yet that one. Okay, I want you to do 10.15.3 right now. .15.3, the challenge activity. If you can. If you don't have a computer, look at your neighbor or help your neighbor. Or do it for your neighbor, yes. Till the exam. Feel free to work together. This isn't a high stakes thing. So this is using find. We could just get a show of hands. Who's done? Okay. Seems like I'll give you another minute or two and then I'll. Pardon? You what?
I misspelled a word.
I was arrogant and thought I knew it from memory. I wrote std : NPOS and got a compiler error when I tried it. So that was a bit of a.
I misspelled censored and darn.
Oh yeah, that was the other thing I did. I didn't capitalize censored. I left it lowercase.
Well, I capitalized darn.
Ah. So we both got caught.
But then I also capitalized censored, I just misspelled it. So I had to go back and copy and paste it.
I gotcha.
Done.
Okay. Okay, so don't worry if you haven't finished. You can do this also on your own time. So here is the solution. So you need to use the find command, and it is case sensitive. So we try to find darn, and if that is not equal to string : NPOS, then it means we found it. So in that case, we print out censored, and otherwise we simply print out the user input. Any questions about that? So you also could have written, it wouldn't be wrong if you had written if user input.find darn equal and string. So in fact, I'll write it at, I can't, this is their solution. If you had written equal string in position, then see out user input, else see out censored, that would be fine too. But the key here is we wanted you to use the string : NPOS to see how it's used. Notice there's no quotes around it. Okay? So the other useful command is replace. Sometimes you need to replace characters at some point in the string. So starting at some index, you want to replace this number of characters with this substring. Okay, so this is another useful command. Obviously, insert is too, but insert, you're simply inserting at the given index. Replace, you're replacing at that index. And what I want you to do is the 15.5.2 challenge activity, which uses replace. And before you start, to save you time, because I didn't bother to read the code, so you might not either, it has already removed the first character of the username, so you don't have to do that. I did it, ran it, and got the incorrect result because I had 2 characters removed. One thing I wanted to point out about the substring command, the second argument is actually unnecessary. In this case, I wanted the rest of the username string. I could have just said username.substring1, and it would have returned the substring starting at 1, and since I didn't give it a second argument, it would have given me the remainder of the string. So if you want the remainder of the string in the substring command, you only need to give the first argument. Okay? One last thing with strings, and then we'll move on to vectors unless you have questions. So it appears from the book that there's two different ways to append a string. One using string 1 plus string 2, and the other using the append command, which is not in this particular section, but you can say string 1 dot append and then a call for string 2. But they're subtly different. They both end up with appended or concatenated strings. But can someone tell me why they're different? They're actually, while in both cases you get a concatenated string, append and plus have slightly different outcomes. And I'd like to make that clear. So I wonder if anyone knows off the top of their head why they have slightly different outcomes.
Mutable versus it creates a new, the operator creates a new string.
Very good. So the operator plus creates a completely new string and leaves the original str1 unchanged. Whereas if you say str1 dot append, passing string 2 as an argument, it will change string 1, str1. Okay? So the plus operator gives you a completely new string, leaving string 1 unchanged. The append command actually appends to string 1, leaving string 1 changed. Okay, so there is a subtle difference between the two. Okay, on to vectors, unless you have questions about strings. Okay, so vectors, again, you should have seen for the most part their use in 102. Did you go over arrays in 102? Or okay, very good. So you've already done the participatory exercises, so I think you're pretty much up on things. I just wanted to show you, though, something that I don't think the participatory activities really went through. So I wanted to show you the dangers, why you often want to use the @ command. So I'm going to create a vector program, very simple one. Remember, you have to include vector whenever you want to use a vector. So I'm going to create a vector of 5 elements. Call it nums. And you can see I'm doing something rather dangerous. Which is I'm writing well past the end of the vector, right? So after we've written well past the end of the vector, I'm going to try to print out some of my values. So this code should actually execute without any errors. Should also compile. It should be clear to you that it is writing well past the end of the vector, right? Hence dangerous. So let's see what happens. I'm hoping that one of these two values is going to get clobbered. No guarantee that my wish will be granted. Okay. And you can see, actually I forgot to initialize anything, so that means absolutely nothing that those values came out the way they did. Notice X is, I have no idea though whether that's because I forgot to initialize them or not. So let's go ahead and actually initialize them. And we'll run it again. And naturally that time it worked just fine. How annoying. Well, that sometimes works and it sometimes doesn't. Basically, here, let's try this. See if I can. And I'll print out foo as well. See if this bleeds over into foo or not. And we'll recompile. Nope, still not bleeding over into foo. This is just annoying.
Add another 0 on the. Yeah. Keep adding zeros to the end of.
To the end of.
for loop.
Yeah, that's a sec. Ah, there we go. Finally, some kind of error. Okay, so you can see that if I mess around with it enough and add enough variables, that writing over the end of it gets me a problem. Okay? In general, you can write past the end of an array or a vector and it won't complain, but it will overwrite memory, which is bad. So you are much better off using the at function, because if you use the at function and you try to write past, it will give you an error and terminate the program. That is much better. Terminating with an uncaught exception of type std out of range vector. Annoyingly, it does not give you the line number that it occurred at, but at least you know that you were out of range with the vector. So please get in the habit of using at when you access integer values. I know it's not as elegant as using array brackets, but it will save you untold grief. Okay, it's much better to have your program terminate immediately when you attempt one of these operations than to have it overwrite memory that you don't expect. And believe me, every semester at the beginning, one of our biggest things that we see in the labs is students using the regular array notation, overwriting memory somewhere and wondering why their program doesn't work. So get in the habit of using at, if at all possible. Okay, another thing. You have to be careful if you, so obviously this would be a lot better if I had written less than a dot size. Now, big thing. Don't say I less than equal a dot size. You do that, you'll write past the end of the array because we start with 0, right? Use less than. Here's a thing that Dr. Planck's notes show and that you have to be careful about. A dot size, or size, doesn't actually return an int. It returns something called size underscore t. So let's see, Dr. Planck's notes. The book also says it. So there's this type called size underscore t. And if you really want to be safe, when you declare your subscript variables for iterating through vectors, you will declare them as size underscore t, or, and I don't really care if you do this, declare them unsigned. So the reason for this, if you remember from 130, unsigned integers can't be negative. Unsigned means no sign, so they have to be 0 or positive, and obviously the size of a vector can't be negative. So C++ made the choice of having the type returned by the size method be unsigned, and to further make their code be unreadable, they decided to create a new type called size underscore t. So my recommendation when you declare your variables for your index variables, declare them as size underscore t or unsigned rather than declaring them as an int. And the reason for doing that is subtle, but sometimes you have to go through a vector in reverse. Here, Dr. Planck is going through a vector, and he's starting at the end of the vector, and he's going from back to front. And if you declare I as an integer, you'll actually get this warning out of the compiler. Comparison of unsigned expression greater than equals 0 is always true. So what you're thinking happens is that I is counting down. Let's say lines has a size of 5. So you're thinking that the countdown goes 5, 4, 3, 2, 1, 0, and then I becomes -1. And when I becomes -1, this test fails and the loop exits. But the C++ compiler is always on the prowl for ways to optimize your program. And it knows that a unsigned variable can never be negative. So what it does is, seeing this comparison, it knows that this is always true, which means you end up in an infinite loop. Okay? So that's what the warning is all about. So in this case, you would actually have to declare I as an int. But in other cases, you're thinking, so why not always declare I as an int? It's because in other cases, you will do a comparison. Let's see if I can find out where. Okay. I can't find it. So I guess the bottom line is sometimes when you're comparing unsigned and signed quantities, you can get funny stuff happening. So in general, when you're doing comparisons with your index variables, you want them declared as either size underscore t or unsigned. But if you're counting back from the end of something, then your index variable is going to have to be declared as an int. Okay, so my recommendation, just declare these things as unsigned or size t, but if you see this kind of warning message from the compiler, then change it to be an int. Okay, so that's what's going on. And it seems to always bite someone somewhere during the semester. Okay, so while we're at it, there is a way to avoid this little nastiness with the I variable, and Dr. Planck hates it, so when you get to 302, you probably won't be allowed to use it. But this is dangerous, okay? Simply because it's very easy to forget that it's less than rather than less than equal. So today I had you reading about the for-range loop, and in this class you're allowed to use the for-range loop. So I have an example of it right here. I'm summing up a vector of numbers, and you can see here's that for loop. So you declare, so what the for loop is called a for range loop, and it iterates through each element of the vector and assigns that value to this variable value. You don't get the indices. Okay, so if the vector contains the values, say 10, 30, and 50, then value will in succession get 10, 30, and 50. And this will assure that you never have an index out of bounds problem. So I encourage you to use it. You notice that you declare the variable to be of the appropriate type. Now you may say, well, what if I want to change that value? Well, I have an example down here. Here I want to read 5 values into this data vector. And what I did was I put a ampersand in front. Remember those ampersand parameters, reference parameters from 102? You may or may not. But what this is saying is that I can now change this value. So when I do the cin into value, it actually changes the value to whatever I just read. Or if I wrote it would change the value to 10. So if you want to change the value, put a ampersand in front of the range variable. Now, if you use this idiom and you try to compile, you'll probably get a warning message because this comes from the CS140 standard. So our compiler and the Mac compiler both are using the C98 standard, 20 years old. Okay? The reason that happens is despite the C11 standard being almost 10 years old, not all the extensions are necessarily implemented in those compilers yet. Okay? These are generally public domain compilers done with volunteer support, so it takes a while to actually get those extensions in. So on the Mac compiler, well, actually what you need to do is I need to look it up. I meant to do C plus, okay, plus, thank you. So give that to me again. D equals, there we go. Make sure that works before I. There we go. So if you're going to use this, you need to use this flag. And I've told Clara, and she already has it in her scripts, that will compile. Okay, so you have to use that flag. Otherwise, it will fail on both the Mac and on our GNU compilers. But it's a lot safer than running an index through it. You can't use it, though, to run it in reverse. So you still have to count down. It only works going up through, from 0 up through the entire vector. Okay, questions about that? Questions about that ampersand operator? Okay. Next thing. You may have wondered why I made you go through the debugging example 12.10. Okay, because it's kind of tedious. It might have seemed obvious too. The reason I made you go through 12.10 is that debugging is one of the most important skills that you can learn. Yesterday in lab, I had you use print statements. So print statements are one way that you can debug a program. But another way, especially still in 140, the programs are simple enough that you can manually trace them. And sometimes that is a very good thing to do. And that's what they were doing, is that they were manually tracing the loop's execution. And it's really hard to get you all to do this. But sometimes when something isn't working, just manually tracing it out on paper really works. Okay? And by the time you get into 302 and 360, it gets a little harder to do that. But I find often manually tracing does work with debugging. So that can really show you sometimes where your logic has gone off the tracks. So that's why I had you read that section, just to emphasize that manual tracing can work. Okay? Also, I'm about to use manual tracing to show something in Dr. Planck's notes that I think wasn't completely obvious. Okay? So he wrote, I think most of his notes are pretty straightforward till he gets to his tail function. Okay? At the very end of his notes, he wants to write a function that's going to return the last n lines or last 10 lines in a file. So that's reverse. So for example, you actually have a tail command. It's part of Unix. And it returns the last 10 lines of the file by default. Or I could say tail 5. It would return, whoops, try tail dash 5. It would return the last 5 lines. Okay, so tail's pretty easy. If you think about the obvious way to implement tail, it's to read in the entire file into a vector and then print the last 10 lines, which is what he does here. He reads them in using getLine, pushes them back. Then at the end, he says, if the number of lines in the file is less than 10, set I equals 0, because obviously you want to print the entire vector in that case. Else set I to be lines.size minus 10, and then he prints out the last 10 lines. Okay, any questions about this or why this 4 omits this right here? Notice that he doesn't have anything right there. It's because up here he already set I to the right value, so he doesn't have to do it there. Now, can anyone think of any possible issues with reading an entire file into your program? Files can be big. And if we only want the last 10 lines, that's a huge waste of memory. Okay, so not only might your program run out of memory, but the runtime environment has to allocate all that memory, and that takes time. Since we only have to print out the last 10 lines, maybe we should declare a vector that's only 10 lines long. Okay? So, Dr. Planck then writes a non-obvious program. So the obvious thing to do would be to actually declare a vector, and once it got to be more than 10 lines long or 10 entries long, you would delete the first entry. In the Xi book today, it showed you how to do that. You can delete any entry. Does anyone know why that is just horrible beyond belief to delete the first element of a vector?
Just to shift them all off.
Because once you're done deleting the first element, you get to shift all the remaining ones one element to the left. So that's not horrible for 10, but it's not great either, especially if you're doing it like a billion times because the file is a billion lines long. It will be expensive. So deleting from the front of a vector is pretty bad, and Dr. Planck doesn't want to show you that so that you don't develop bad habits. But instead, he shows you a clever program, but he doesn't trace it. And I think it might help to trace it to see what's going on. Okay? So I'm going to show you the general idea of what he's doing. I don't want to use 10, I'm going to use 5. So, whoops, don't want that. Nope, don't want that, want that. Okay, whoops, why am I backwards? Because my tablet's backwards. Okay, let's go back up here. Okay. So let's say that I want the last, and you have to just bear with me, the last 5 elements in the file. And let's say my file contents will just be very simple. So it should be pretty clear we want to print out 3, 4, 5, 6, 7, right? Okay, so what we're going to do, we're going to start reading in numbers. And the first 5 numbers are no problem, right? Now the question is, what happens when we read in 6? Well, what number do we no longer need? 1. So what we can do, and it so happens that 1 is at the beginning. So we go back here and we put the 6 where the 1 would be. Then we read 7 and what's no longer needed? 2. Okay, if the file was longer and had an 8, where can we put the 8? 3. So it should be pretty obvious that what we can do is wrap around to the front of the vector, start writing over the contents of that vector. If we got to the end, so let's say the file was even longer. Now I'm going to make it 9, 10, 11, 12. We would write over 4 with 9. We'd write over 5 with 10. And again, we'd go back to the beginning, write over 6 with 11, and write over 7 with 12. Okay, so what we want to do is keep wrapping around the end of the vector. So how does he do that? Well, here's how. He starts and he's reading lines, and as long as the lines are less than 10, he just does a pushback. After 10, he has to wrap around, and he uses the mod operator. Because the mod operator, modding by the size of the vector, will get us back to the beginning. So on line 10, which is really line 11, so when ln is 10, it will be knocked back to 0. When ln becomes 11, the index is 1. When ln gets up to 20, it's again wraps around to 0. Okay? So this is a cute trick that's often used with arrays and vectors, where you want the vector or array to be a fixed size. It's called a circular vector or a circular array. It's the name you'll often hear for it. Okay? So at the end, you have your numbers. So let's say I'm done. And my entries are 11, 12, 8, 9, 10. Clearly, we can't start printing from the front of the vector because that doesn't give us the right order, right? It gives us the last 5 lines, but not in the right order. So when we're ready to write out the last 5 lines, we also need to know where to start. Okay? Well, in this case, let's just think where ln would be. ln would be pointing right here, and at this point, ln is going to be 12. Okay, or is ln going to be yes, it's going to be 12 because he's doing a plus plus. So when he's done, ln is pointing to the next available free entry. Okay, so he sets ln to be ln minus 10 because that will get him back to the right place. Okay, in my case, I would set it to be ln minus 5. And then he goes through, and if it's less than 0, it means he didn't have enough. So if there were fewer than 10 lines in the file, I will be less than 0, so he wants to print out everything. He sets I back to 0. Otherwise, while I is less than ln, he increments it and uses that same idiom. So basically, it's just like you would think. He just resets ln back 10 lines, and then he starts counting up and printing them out. Okay? I don't claim that's clear. I do claim it becomes a lot clearer if you're willing to put it down on paper and work it out. Okay? So part of this is to try to show you that sometimes when things look a little tricky, if you just put it down on paper and work out a simple example, it might make more sense rather than just trying to figure it all out in your head. I'm a big fan of using concrete examples on paper. Okay? And I have 10 minutes, so I can pontificate for a couple minutes. I think this also helps a lot when you're trying to figure out how to solve a lab problem. So when you're confronted with having to write a program in lab, you would be surprised at how often you can pretty much figure out the program if you take a simple problem with some simple input and work it out on paper and figure out how would I work this problem if I were just doing it in my head or on paper. If I didn't have a computer, if all I had was paper and pencil, how would I work this thing out on paper? It turns out that in general, the solution that you would use on paper is the same solution you would want to program up. And you'll have to have some data structures normally, like you normally would keep a list of things. Well, that list just becomes, in the first few labs, a vector. Okay? So not only does working the problem through on paper first help you better understand it, it also generally gives you a blueprint for how to actually write the program. So I'm a big advocate. Often if you come to me for office hours and you don't know how to start writing the program, I actually give you a small example and make you work it through with me on the whiteboard. And then I say, okay, how do you reduce that to a program? So I am a huge fan of using paper and pencil to work things out. Also, if you don't understand a tricky piece of code, and I claim that Dr. Planck's piece of code is elegant, but if you've never seen a circular vector before in your life, this code probably looked pretty gnarly to you. If you hadn't, and if this is your first time looking at it, because you didn't look through the notes, it's probably pretty gnarly. Okay. Any questions about vectors or about strings or even about what you saw in lab yesterday with lab 0.5 or lab 1? Okay. In that case, I will let you all go, and I will see you all on Thursday, where we will be doing something, but since my computer is currently messed up, I can't get to it.
I have a quick question about the homework.
I think you mentioned.
So, I'm trying to find